want to start by thanking you for inviting me here. I really appreciate the opportunity to present some of our works about structural and also infrastructure part of the design. This is a distinguished audience. I hope I will reach the level of your previous presentation on future. I started. Where is this one? I will, I don't know. Yeah, it's working. In short, I will introduce some pictures and some thoughts about the earthquake in Vrancea from 1977. I will give you a short description of the structure itself. We found the uplift and pounding, the challenges of our design. We will look a little bit to geotechnical findings, and then we look a little bit on the complex condition of computing modeling, and we draw some conclusion. We didn't have any major earthquake in Romania since, let's say, 50 years, because the 1977 was the only, let's say, important earthquake generating lots of destruction. I put here some pictures on the screen. There is lots of out of plane masonry collapse. In the middle, you can see there was a collapse because of the shear forces in the columns, and also a part of the building collapsed. It is difficult to predict the next magnitude of the earthquake, so because we have only one real big earthquake, which was magnitude 7 point something, and it was recorded. The other ones, they were not recorded, so it was one in the 1940s, and it was not recorded because the seismometer broke on the magnitude. It is really important to underline that for the 1977 magnitude earthquake, we had some 1,600 fatalities and 11,200 injured. Moldavia and Bulgaria, neighboring countries, were affected by this earthquake, so it was quite a large area felt earthquake. And also it was felt even at Moscow and Istanbul. It is important also to underline the economic losses. Economic losses were worth at that time of $2 billion USD, which were 70% of the total damage was direct losses. The earthquake destroyed 32,000 buildings, and 33 of them were high-rise building. 35,000 families remained homeless. This is very important. We recently, all of us saw on the TVs, like the recent earthquake in Turkey, people were displaced, they were homeless, staying in tents and so on and so forth. This was a national disaster. Total reported damages, including direct and indirect damages, were 7.25 billion lei, which is roughly 4.5 billion USD at that time. But most important, it is the amount of the total economy of Romania, which was huge. It is in between 13% and 21% of Romania in GDP at that time. This led to a really bad time. So the crisis started like 2 years after the big earthquake, and it was prolonged like 10 years, and it ended up, for our fortune, with a revolution in 1989, which is a nice outcome from a bad situation, let's say like that. I would like to underline, flickering through the picture, I would like to underline there is something which struck me. Usually we thought like the damage or the collapses were due to structural collapse. But if you can see it here, you will see that there is an inclined infrastructure here. So this might be a geotechnical failure as well. This, the habit of construction in Romania at that time was RC shear walls, really stiff. So it might be feasible that the soil was giving away as well as the superstructure. Taking into account what I started to say, it's just a question with which we started the design I will present in the followings. How can you do to better perform for immediate occupancy? Immediate occupancy is, it means that we can retake our lives. In my opinion, the designing codes are quite well designed at this moment. We are not anymore fear about human losses, maybe some accidents, but not so many. But after the big earthquake, we can, let's say, expect really big damages in the buildings we are living or on the construction we are using, like bridges, hospitals, and so on and so forth. So what we can do at least with our knowledge for today, either we design for elastically behavior of the structure, which means really high, huge acceleration, or go for seismic isolation or added damping. I always liked this FEMA table or FEMA chart. You can see from top to the bottom, whichever system of structure you will apply. It means starting with the left column, you will see some ambulances. The ambulances for the seismic isolation system, it's not present. Whereas if you don't do anything with your building, you will have lots of things. But from left to right, you will see that the money you put in the house will increase, but also the savings in the long time will be higher when you apply a better solution or a modern solution for the structural protection. What we are talking about right now, it's the design of a high-rise building. It's 100 meters above ground. It's the right building in the picture. It consists of 2 towers on the common infrastructure. The 2 towers, the left one, it's 12 floors, and the right one, it's 24 floors. There are 2 basements under those buildings, and in between them there is a small building of ground floor and 1 story. What we did for this structure, we would like to be a nice structure, and so although Romanian code is right now, but it will change, having a recurrence period at 225, we went for 475 as Euro code specified as well. And what is very important for us, it's just the corner period. You can see it here on the top part, on the right. It's 1.6 seconds, which is quite large. It's usually for soft soils, and Bucharest has some of soft soils. The rest of the parameters governing the design are quite usual. We had an importance class because it's a high-rise building of 1.4, and also we used a behavior factor of 1.5. The ductility class chosen by code, it should be L, but low ductility, but we did some medium ductility approach because we wanted to be sure. We wanted to put some extra safety in the structure. The layout of the structure itself, it's a central core with walls, RC walls, and there is a moment resisting frame on the perimeter, which is also RC. The dimensions of the structure resulted quite impressive, like the walls, they had up to 80 centimeters width, and also columns in the basement were like 1.3 meters diameter, and then on the upper floor they have reduced somehow. You can see all the layout on the basement. On the basement, they were not frames. We just kept the columns. It is important to, or maybe it is to show a little bit of a detail here, which meant like the left tower, the smaller tower, had to stay in the corner of the excavation. So since the pressure of the soil it's already there, we had to improve the support of the structure and also allow some movement. So that's why we came up with some kind of struts, and here it's a lattice girder somehow in concrete, horizontally placed. This is the schematics of the structure as it was designed. You have the seismic isolated interface in between the rough foundation and the superstructure, and we have gaps in the infrastructure in between the moving part, which are the two towers, and then the fixed part, which is the middle and the exterior part. This type of approach resulted not because we wanted this position, but because the architectural design was readily at the moment we started the structural design, as usually is in Romania, and they were quite reluctant to change anything, so we came up with this idea. This idea posed, in the end, two more challenges, because as the building over the ground, it's almost 100. When we added some basement levels, it went up 100 meters as height to be isolated. Also, the interesting part, it was at the end of the story, because we put so many seismic gaps. It was a real challenge in the end, as a price-wise, to fill the gaps, because the let's say the client wanted a very nice and posh treatment of the gaps, not just simple. This is the layout of the isolators. We went through many iterations to try to get a better understanding of how we can find, let's say, an optimal placing of the isolator. Some of them I will discuss them later on. We put some piles under them. We try to concentrate the piles, like 4 piles on each isolator, and this is the overlay in between them. The isolators were, the seismic isolators were double friction pendulum type, because we needed a really large isolated period, we will see later on. And usually the rubber bearings are quite stiff, and you need to do some combination with that sliding. So we put the isolators directly under the columns, but on the central cores, we will see later on why. We prefer to put it on a thick slab, which is more or less like another foundation raft. We perform like 7 natural, we used 7 natural recorded accelerograms. We used from Romania the biggest 3 recordings, but I would like to underline this, because the March 4, 1977, it's the line, the big line. Usually all the small lines are the other ones, which are not even half of the energy in March. You can see them. You can see the peak of 77 and the other one, even if in magnitude they are not so different, in energy they are really different. So in order to capture better the idea of long period motions, we used some Japanese movement, which are like 2 and something or 3 and something seconds main corner period, and also one from Iran. In the end, we matched over the spectrum, so you can see here how they liked in the design time. We were able to have a quite nice distribution of vibration, because you can see first mode it's 5 and something, second mode it's 5 and something again, and even the torsion it's 4.5, it's also around 5 seconds. This is very, very nice, but that I would say it's not our merit, it's just the geometry of the building. It's you can see it's square, and the distribution of the structure, we were allowed to put it really nice. I will stay a little bit to these graphs, because they will summarize somehow what we try to do with the superstructure. You can see the magnitude of acceleration from elastic response spectra. It's 12 meters per square second, quite big. It's 1.2 Gs. So moving, it is true. The lower tower would be here in the main period of vibration, but the high tower would be somewhere here in between 2 point something seconds as a main period. So for the lower tower, it was really a big gain, because we started with 12 meters per square second, and we end up with 1, but adding the damping, I'm sorry, with 1.53, adding the damping, we went to 1, and in the superstructure, we could even get a lesser design acceleration, which is 0.67, because of the Q factor we are able to do. So it's the most efficient way of reducing the acceleration in the structure. I would like to make a short parenthesis. It's not the structure itself. Maybe you can understand better, because we are thinking also about the occupants and the secondary elements, and also about all the machinery, maybe, or the things we have in the buildings. High acceleration, if we design, like I said, for high acceleration, like 12 meters per square second, you can imagine always that you can, if in case of an earthquake, the things in the building will fall laterally with 1 point something G, which is really huge. You can just reverse the house and you understand how big are the forces if you design elastically, which is not feasible. In terms of displacement, we just reduced from almost 1 meter displacement demand. We got 0.63 centimeter, the final design. This is the a picture from the design stages from the ETABS model. The maximum displacement in the isolator was 590 millimeters on one direction, but combined it's 720 millimeters. I would like to invite you to look at this value, which is 1.3 meters. It will be the displacement, total displacement in the isolation interface and also in the building itself. There is a comment here. All the, let's say, differential displacement in between the story levels was like 1% from the height, which is quite well, because the limit in the code is 2.5%, and the limit for the service limit is 0.5 for brittle cladding and so on and so forth. But from this one, part of it will be it's due to an rotation of rigid body, which is not really impacting the rigidity or the damage of the things inside the buildings. So this is the building we are talking about. It's 30 meter wide, but 105 meter high. This is a ratio width over height, it's 3. Overturning, even if we look at it, it will be most probably. And it went. In the design we found that, for example, the 1977 earthquake gave us an uplift after 18 seconds. You can see here, this is the compression in an isolator, and this is the deflection in an isolator. Compression, it's on the higher part of the line of the graph, and also the uplift, it's also in the higher part. So you can see here, there is no force in vertical force in the isolator, so it corresponds with the uplift in the isolator. Okay, let's see what happens. There is not a new situation, this one. You can have a not so stiff base, like base isolation, and then if you don't connect the structure itself with the base, you'll have also some rocking. I think also Professor Pitilakis talked a little bit about it in another let's say context, but it's the phenomena, it's more or less the same. If you are able to induce some rocking on the base of the structure, you won't put so much energy inside the house, which is, I would say, very advisable. I'm not in favor to tie very stiff the structure on the foundation themselves. Here you have a basic representation of the isolator curve, basic backbone curve. It's being a sliding isolator. You can see in this middle part you have sliding, and then in the end part you reach with uplift. What important things comes with the uplift? You can see this is a simple model, but just for understanding, all the weight will go in one point, let's say theoretical point, which will put an really important stress on the whatever system of foundation you design. But more importantly, when the building comes back, it will be really important to see how it will pound. The stiffness of the support here, it will be really important on the magnitude of pounding, because if it's, let's say, if you consider it as a fixed point, this will imply an explosion and the destruction of everything over there, because you cannot dissipate energy if you have a fixed point over there. So there is the bigger problem. This is also a slide a picture from the ETABS model. You can see almost half of the building was uplifted. It was really interesting for us. And we summarize here all the, let's say, the variables which are in place for this structure. For example, piles. Piles, we need a lot of things to think about them, because we need to think about the lower bound, the upper bound. We thought we used this GCR. For our code, there is only one value for static analysis. Plaxis model, we try to also reach some understanding from that one. Soil also, it's a variable, but because it will, we saw that it's not really important in the total equation, we neglected the variation of it. Foundation raft itself, the stiffness of the foundation, slurry walls on contour had some importance for the stiffness of the infrastructure, stiffness of the superstructure itself, also RC slab and beams. They usually are designed with 50% of their stiffness in the seismic event. But since this was an base isolated structure, we didn't think that the 50% stiffness will be reached, because the damage in the structure will be really neglectable. So we used lower values for the reduction of the superstructure, and also friction on the surface posed a lot of other variables, because there is the pressure on the sliding surface. It really depends on the vertical forces, because you can see here the producers, they give you really different values. So you will see something which is counterintuitive. When you get higher pressure, you got lower friction coefficient, and vice versa, which is at first, when I saw it, a little bit confusing. And then temperature, slide and velocity, and there is also an upper and a lower bound due to the fabrication process. In this, taking into account all those variables, we looked a little bit, as I previously said, of how much proportion of the weight of the building goes into the foundation and how much is carried by piles. And we concluded that because of 85% of the weight of the structure or the loads are carried by piles, and 50% of the loads from the structure are going into soil, it's not really important to go in design-wise into that direction. We did a Praxis model also to be sure that we can have all the things in hand, because we used from the Praxis model, we deduct a bilinear spring for the model to describe the behavior of the piles. That vertical stiffness, it was really important, because if you go with, it was really different as values, because what we had from American code, it was really another league as a stiffness. We have like 2,000 meganewtons per meter and 1,500. Those were big piles, 1 meter diameter and 50 meter length, and also 1.5 diameter pile with 50 meter length. But what we saw, because you can see the vibration period is 5 seconds, we saw that the variation of the stiffness because of dynamic condition was not so big. You can say it's almost static, but not quite. Because of the model and the time limitation, everything else, we tried to just compress the model, and we developed a complex model, and we studied only for one accelerogram, and we combined here everything into under the seismic isolator. Those points are seismic isolators. So we just did some iteration to combine everything into it up to the moment we find the satisfactory convergence. During this time, we discovered some interesting thing. So because we firstly put all the isolator under the central core, the pounding was so big that we received some 70 meganewton in a corner isolator, which was really huge, and we were not able to find the testing machine, even in United States, to reach this value. So we thought about other ideas. So in the end, that was because we thought, what happens when the high margin of the stiffness will happen, and when the high margin of the stiffness happens, the pounding was really big. Because of that, we changed the layout of the central isolators to this one. We filtered, somehow we filtered throughout structure the amount of forces which can get into the isolator through this, let's say, type of raft over the isolators. And throughout its bending, it will limit the amount of forces you can put into an isolator. This is the complex model in the simplified way. We put springs, series springs for its isolator, cap, foundation, slab raft. And then the piles and the soil, we combined it in parallel. We reach with an unique spring, and we combine everything once again in series. The stiffness, we found it's some here, I just don't remember by heart. Rough foundation 74 kilonewton per meter, and then for piles we have 1.8 meganewtons, pardon me, 7.2 kilonewton per meter. And this is what we reached for example, for equivalent spring nominal value was 5.21. For the lower part, because it's not clearly half of it, it's 3.02 E6, and then for the upper bound it's 84.16. This is the table which summarizes the results. You can see it is not really clear, but I can tell you that the let's say the values obtained for the lower margin, the nominal and the upper margin were quite close. You can follow it here. It's like 45,000 meganewtons, and then it's 43 here. So the system we proposed, it really worked. It filtered throughout the bending, the stiffness. So in the end, we used also the static stiffness for understanding the magnitude in the pounding, and we received quite well distribution, because we saw that it's not really dependent right now of the stiffness of the piles, and also we didn't receive like really high uplift, because the energy of pounding will also depend on the height of the uplift itself. I will finish with the conclusions. So maybe I can read them, because I would not like to say something wrong. When addressing complex problems, the stiffness of the foundation system becomes critically important. This could be also important for the safety, but also for the savings. Anyways, other further certainties makes the problem even more challenging to solve. Step-by-step calibration models are usually necessary to bridge interdisciplinary knowledge, combining theoretical insight with computational technologies. And for a successful design, safety must not be overly sensitive to wide variation in input parameter values. I would like to say that even I described this building and we enjoyed to design it, it was never built, because it was, let's say, it went into a process of value engineering. So usually in Romania, value engineering means cutting costs, not other than that. So we end up on designing a version of damped structure instead of base isolator, but they still sell it as base isolator structure. So I end up with saying that I sincerely appreciated the opportunity to have your attention. Thank you so very much.